Hi, today we are doing partial fraction decomposition. And basically what we're talking about is decomposing or breaking down an answer that was given to a rational expression problem. So two fractions added or subtracted together. We know that we can break an answer down into those two fractions or a possible set of fractions that created that answer. And that's what we're doing when we're decomposing. So we're taking the answer, which we're starting with here, and we're breaking it back down into a possibility of two fractions that were put together to create it. And so this is a partial fraction, this is a partial fraction. The two partial fractions together created that answer. So we are going to work through 5 examples today just to make sure that you're good on this topic. And so I'm going to write out or talk about most of the steps and where you can kind of cut steps and where not. But as with anything, the first couple, we typically put them all in our notes. So the first problem we're going to do is actually recreate that example that I talked about a minute ago. So here's a problem I'm starting with. So the first step is to factor the denominator. So I take my denominator, I factor it into linear factors. We are only going to focus on linear factor denominators this year. So everything should break down into some sort of linear factor. Once we have the breakdown, then we're going to separate this back into multiple fractions. And so what I'm going to do is I'm going to put one factor in the denominator of each fraction. So x minus 3 is going to go in one of them, x plus 2 is going to go in the other. It really doesn't matter which order you put them in, but you just want those factors separated into fractions. After we have however many fractions we need for our particular problem, then we're going to assign a variable to the numerator, because that's what we're going to do now, is we're going to solve for a, so we know what the top of this fraction looked like, and we're going to solve for b because we know what the top of this fraction would look like. So to do that, I need to get rid of my denominators. And if you remember back in Algebra 2, we learned how to get a common denominator and how if we used that and multiplied it to the fraction, then it would multiply to this and it would take care of that on the bottom. So that's what we're doing. So I can divide or multiply each piece by x minus 3, x plus 2. And when I do that, when I have this times this fraction, the denominator is going to cancel and eliminate. When I have this times this fraction, the x minus 3 in the LCM or the least common multiple and the denominator are going to cancel. And when I have this one, the x plus 2's are going to cancel and leaving me with that. So when I pull what's left out, I get an x plus 7 from this side of the equation. I get an a times x plus 2 from this side and a b times x minus 3 from that side. So this is my substitution equation. So we want to definitely have the substitution equation in our work. All right, so now that we have a substitution equation, what are we going to substitute in? We can be smart and pick good numbers that make our life and calculations easier, or we can just pick any number. Any number is probably going to cause me a more complicated process. So the good numbers to pick, the ones that I want to select from, are the ones that would make any of these denominators turn to 0. Because if it makes the denominator turn to 0, then it's probably going to zero out something in my substitute equation. So this can be 0 when x is 3 or when x is negative 2. So let's start when x is negative 2. So I'm going to plug in. So I always have to make some statement about what I'm doing. So I'm saying, okay, let x equal negative 2. Then when I plug in a negative 2, everywhere in this equation, this is what I have. So when I start cleaning it up, I go, okay, well, negative 2 and 7, that's easy, that's 5. But look what's happening right here. Negative 2 and positive is actually 0. 0 times anything is 0, so this whole term just zeroed out. So over here I have negative 2, negative 3, which is negative 5. Negative 5 times b is negative 5b. And then I can easily solve for b by dividing both sides by negative 5. So that's one substitution, and now I found the numerator that we have assigned the letter b. So now I'm going to plug in my other one, which was negative 2. And when I do that, I plug in negative 2 for all those x's, or sorry, positive 2 for the x's. Positive 3. Good grief. Sorry about that, guys. It just says right there too. You'd think I could follow my own directions. So here we go. I'm going to plug in 3 for all the x's. So I have a 3 here, here, and here. And 3 minus 3 makes that 0. So b is going to 0 out. I have 5a from this part and 10 from this part. So a equals 2. Do be careful, guys. I'm still having a few people that instead of dividing both sides by 5, they're dividing by the number over here, which gives them the fraction 1/2, which is most definitely not 2. So now that I know what my a is and I know what my b is, then I go back to those original equations where I had an a and a b, and I plug them in. So I put the a where my a was and the b where my b was. It doesn't matter which one you assign a or b, because you're going to solve wherever that a is in that instance, and you're going to put it back where you assigned a to b. So, you know, it looks like it should be different, but it isn't. So you just solve for wherever your a is, and you substitute back into wherever your a is. All right, so this is a decomposition. So I'm going to have my original problem equals, and then with the numerator a being 2 over x minus 3, and the numerator -1 over that. You could say -1 over x plus 2, but I'm fine with either. You know, you can always check your answer. You can add these two fractions together, and you can see if you get the other side. So there's really not any reason to ever wonder if you're correct or not, because you can check everything. So decomposition, remember then, is the reverse process to performing operations with fractions. So we're starting with an answer, and we're finding what the problem could have been in the beginning. Okay, so for problem 2, let's keep doing what we're doing. So the first step was to factor the denominator. And so I did that. And that was the difference of squares. And then I broke up however many fractions I needed, which was 2, because I have 2 different factors here. Then I assigned the variables to the numerator, so I made this my a and this my b. So now that we do that, we want to get rid of those denominators and create our substitution equation. So I multiplied the top of the bottom, or this fraction by x minus 1 plus 1, x minus 1 plus 1, x minus 1 plus 1. In this case, everything eliminated but the 1. In this case, the x minus 1 is eliminated, leaving me an a times x plus 1. And here, the x plus 1 is eliminated and left me with the b times x minus 1. So that's my substitution equation. So once I have my substitution equation, I need to do a little bit of substituting. And I do that by picking smart numbers. So I know x can be 0 when, this can be 0 when x is 1, and this can be 0 when x is -1. So those are the values that I'm going to plug in. So I let x be equal to 1, and I plug my 1 into the substitution equation. The b zeroed out. I was left with 2a equals 1, so I know a is 1/2. And then I have x equals -1, plugged in my -1s, a zeroed out, so I found b equals -1/2. So once I have my a and my b, I go to my equation. However, this one looks a little strange because you have fractions in the numerator of a fraction, which means we have a complex fraction, and we don't leave answers in terms of complex fractions. So I think one of the easiest ways to think about this is think about your rational expressions, and if you have a vertical stretch or compression, that's the same thing as a times the fraction or a in the top of the fraction. So if I think of this as a times the fraction, I can pull the 1/2 down in front and multiply the two fractions together. So I get 1 over 2x minus 1 and 1 over, and notice the change from a negative to a positive here, adding to a negative because of that sign. And I have this. So all I need to do to wrap it up is just distribute it out. And so I get that. And that's my final decomposition. So you need the original problem, equals, and the things that it broke it down into. Remember, when you're working through these problems, you can always pause the video, work the problem, and then compare your answer to mine. So if I'm going and talking through it a little too fast and you need a little pause time in there, just pause your video and make it happen. All right, so I told you we were only going to do linears, and sometimes I get students that look at this problem and go, hey, wait, but you said it was only going to be linears and there's a quadratic. Well, if I factor this down in step 1 like I'm supposed to, then I can see that I have all linear factors because that's the difference of squares, and that's x minus 1 plus x plus 2, or x minus 2 times x plus 2. So now I have 3 denominators, so I have 3 fractions, and I have 3 variables. So this time now I'm going to have to solve for A, B, and C. So I need to get my substitution equation. So I'm going to multiply everything by x times x minus 2 times x plus 2. So everything here cancels, leaves me with 3x minus 1. The x's cancel here, so I'm left with x times x minus 2x plus 2. The x minus 2's cancel here, so I'm left with bx times x plus 2. And the x plus 2's cancel here, so I'm left with cx times the x minus 2's. And then I'm going to pick good numbers to work with, so I'm going to let my denominator equal 0, so I know that's going to happen when x is 2 and x is negative 2. So I can also have a 0, though. Don't forget that factor right there. So I'm going to start with 0. I plug 0 in everywhere, and then my number zeroed out, my b zeroed out, my c zeroed out. So it was very easy to solve for a. Then I used 2, and I plugged a 2 in everywhere that there was an x. And I noticed that my a's and my c's zeroed out, so I have 5 from this side. And when I clean this piece up right here, I get 8b, so b is 5/8. So now, last one to try is the negative 2. So when I substitute in negative 2 for all of the x's, the a zeroed out, the b zeroed out, because 0 times anything is just 0. And then we get the... So once we get down here to c, we can see that that's going to be negative 7/8. We have a fraction situation again. And I don't want you to think they all happen to be fractions, but I just wanted you to have enough practice here that you won't, you'll know how to handle it if it does pop up. So we're going to drop that 4th down and then distribute through the bottom. And so, excuse me, we get 3x minus 1, and we multiply or distribute this through, and we get that. And this could be, usually it's probably the original equation, but it's technically not wrong if you write down the factored version. I would probably prefer just the original, but I could take that one either way. And so that's our decomposition. All right, we're on problem 4, and don't forget when I'm doing my notes and I load them, you'll have my notes and my speaking stuff that I would say to you over here on the side too, but I'm not going to take time to try and read stuff to you while we're going through the video. So this is a little different from the other ones because you can see that this means this is powered square. So I have 2 of these. So when I'm looking at the factorization, excuse me, then I have 2 fractions over here. Now this is the one that's different. This is a repeated fraction. So whenever we're allotting for a possibility, because we could have had 2 fractions where this was in one denominator and it had one fraction that just had x minus 3, and this common denominator would still be the same. So we kind of have to allot for that. So what the rule here is when you have a repeated power, you are going to have one fraction for every power from where it starts down to 1. We wouldn't obviously worry about 0 because anything to the 0 power is 1. So I'm going to have a denominator with 1x minus 3, and I'm going to have a denominator with 2x minus 3. So this would be the power 2, and the next power down would be 1. And so everything else is the same. I assign the a and the b. I multiply to get rid of my denominators. I generate my substitution equation. Okay, so nothing there except just remembering you have to allot for that power. All right, so then I only have one value, though, that I can substitute in, and that's 3, because all of these are the same factor, right? X minus 3, 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 a whole lot of x minus 3's. All right, so when I plug in my 3 and I let x equal 3, that zeroes out my a's, and I'm able to solve for b. The problem now is I don't have any other value to plug in because all of the denominators are the same. So this is when it's kind of like a system. Remember when you solved a system, you'd solve for x, and then you take x and plug it back in and solve for y? Same thing here. We used our x to solve for our b, and now we're going to plug our b back in to solve for our, not a, but not y, but a. So here's a technique I want to point out because this kind of pops up a lot. Can you see when I put in my 9, then I'm going to move the 9 to the other side, and then I'm trying to solve for a. Well, what do you notice that these guys right here have in common? They have a 3 in common. I could pull out a 3, And then I have, when I pull out a 3, I have x minus 3 equal to a x minus 3. So when some people go straight to here and then they're like, oh, I'm not sure how I'm going to simplify that. But you don't really have to, right? Because if this is an x minus 3 here and this is an x minus 3 here, that property of equality says then that a would have to be equal to 3. And so that's where we factor that back out and we plug it back in. So now we have an a and a b, so we can go to our fractions and we can plug it in. It's a song from the commercial, plug it in, plug it in. So here we go. We have the 3 is what we got for a over the x minus 3, and the b is what we get over the x minus 3 squared, and that's our decomposition. So this is how you handle repeated factors when you're doing your decomposition. So on this last problem, it's a little bit of everything. So I would recommend pausing the video right now, working through the problem, and then comparing it to me working through the problem and see how you do. Okay, so hopefully you had time to work through that. So we're going to go through the same process as before. We're going to factor the denominator. And so remember, when we take out the x squared, that's the same thing as x times x. So this is a repeating factor in the denominator. So I need a fraction for x squared, and then I also need a fraction for x to the power of 1. The highest power all the way down. So I end up with assigning my a over my x, b over x squared, c over x plus 1. So again, power 2, power 1, there's your repeating decimal. Then I get rid of my denominators by multiplying all the fractions by x squared times x plus 1, which leaves me with the substitute equation of 4x squared plus 2x minus 1 equal to ax, x plus 1, plus b times x plus 1 plus c x squared. So the numbers that can make my denominator turn to 0 are 0 and negative 1. So I began by plugging in negative 1, which caused this to 0 out, this to 0 out, this to 0 out, this to 0 out. So I get a nice easy negative 1 equals b. Cool. Then I try when x equals negative 1. And so I get negative 1 squared, which is 1 times 4, minus 2 minus 1, which gives me a nice 1 on this side. This zeroes out. This zeroes out. Negative 1 squared is 1, so easily get a c. The problem is I need to find a third numerator, and I don't have any other things to plug in. So what I do at this point is use what I know about substitution eliminations, because if I have solved and gotten a b and solved and gotten a c, then I can plug in c and b to find my missing value. So that's what I do here. And there we go. So I replace the b with a negative 1 and the c with a positive 1. Notice I still have an a and I still have a whole lot of x's. So this side hasn't changed. Nothing canceled or zeroed out. And so I have the negative 1 for my b here and the 1 for my c here. So I distributed the negative 1 through and got negative x minus 1, and 1 times x squared is just x squared. So remember, I'm trying to solve for a, so I'm going to move the x over, I'm going to move the 1 over, I'm going to move the x squared over, and I end up with 3x squared plus 3x equals ax times x plus 1. And again, this is going to be like that technique I showed you, because of what do these have in common. You can factor out an 3x times x plus 1. Over here I have an ax times x plus 1. So if I divide both sides by x times x plus 1, the x's and the x plus 1's cancel, and I'm left with that nice a on this side and that nice 3 on that side. So now I know what all my numerators are. I found a, I found b, I found c. I go back and put them in the correct equation. We don't want to plug an a in for the b or anything like that. And so my decomposition, the original problem, the 3 fractions that I created to decompose with, and then the a's, the b's, and the c's that fall back on top. And that's how we do our decomposition. All right, guys, you all can always review it again and work through a problem again, but hopefully you see that it's kind of systematic. We do it the same way most times. Most folks kind of like this topic because it isn't varying much. You kind of use that same process. of factoring, creating your fractions, getting the substitute equation, plugging in values to find your numerators, and then writing your answer. Thanks, guys. Bye.